Well, hello Cinemeric Nation, and welcome to the 2024 Christmas special. I'm your host, Chris Pollock, and today we are going to make a snowman. So now, with the snowman, unfortunately, give me a second, I need to mute my computer over here. You know, there's always something I forget about with these events, so you probably didn't hear it, but it would have drove me crazy the whole time. So with the snowman, traditionally I always like to obviously machine the ornament, right? Whatever we're doing. You can see I got a whole pile up on the top of the machine we've made over the years. Unfortunately with this one, the cycle time, it's a little too long for me to machine this in a half-hour event. I would challenge those that are logged in, if you have any idea or thoughts on how long it would take to cut this part. Throw them in the chat. We'll see who gets closest, and then I'll let everybody know here in a little bit what the cycle time was. I do have Dan Vitullo. He's actually in my ear, and he's going to be kind of monitoring the chat. So if any kind of questions come up, anything you want me to go into more detail on, or you just want to say hello, he'll keep an eye on that so I'm not looking at the screen the whole time. So what I do want to do, though, since we can't fully machine it, is I wanted to go through the kind of the machining process, right? The CAD/CAM process chain. What are some of the tricks that I would need to leverage when I'm going to machine a part like this on a 4th axis machine? You'll have to excuse me. I've been fighting congestion, so I'm trying to keep from going into a coughing fit here on the event. So I will be drinking a little bit. And if I start coughing, I apologize already. So I want to kind of talk to you guys a little bit about just some of the techniques that come into play when I start machining with a machine that has a 4th axis. You know, there's a few different things you want to think about, a few different things you want to set up. So we will take a brief look at how I kind of brought it in, set it up in my CAM space. I did program this all CAM. You get to something of this, any of these kind of free-form geometries, you're really not doing this at the control. This would certainly require some form of a CAM system. We are going to talk about the process of how I evaluated it. I'm going to use Run MyVirtual Machine to kind of go through and validate my toolpaths. I did a little thing where I actually was able to kind of prototype it on my printer. We'll talk about that. And then we're going to get into some real-life machining challenges or scenarios that you want to think through and things that you have to make sure you've set up in the post properly to be able to handle this type of a machining operation. So step one is, where did we get the model? How did I actually do the programming, do the overall setup to get to the point where I could start machining it? Now, in an object like this, I certainly did not have the time to go through and model this. There's a lot of man hours that would go into creating an object like this. So what I did was I actually leveraged a community called GrabCAD. If you're not familiar with it, check it out. GrabCAD, as it sounds, GRABCAD, online. They have a full kind of library of all sorts of different models, from real mechanical parts to nice little intricate parts like this. They're all free to download, and it's a great resource. So I did grab the model from GrabCAD. From there, I brought it into my CAM system. I did do a couple tweaks or changes just to make the machining process a little bit simpler, and then I set up my strategy. Right, so here we can take a look at the first step. So first step was to bring it into my CAM solution. Now, I do use a couple different CAM packages. Certainly I do a lot of stuff with NX. In this case, I decided to use Mastercam for this part. So we are going to look at some of the Mastercam strategies. Why did I go with Mastercam is probably the first question you're thinking. Two primary reasons. One, we've done a lot of collaboration with Mastercam on the 3 and 4 axis posts. They are available in the Tech Exchange for download. So I knew already the features and the challenges I was going to run into on this part had already been developed and anticipated in the post, so I wanted to be able to use that. The other thing that I do like about Mastercam when you get to 4-axis toolpath is as long as you have the multi-axis option, then the system will actually allow you to use advanced toolpaths, which would be typically used in 5-axis orientation, in a 4-axis scenario on a 4-axis machine. So it just gave me a real wide library of toolpaths I could use on this part, and we're going to explore some of that. But step one was certainly bringing the model in, doing a little bit of setup, Now I did tweak the model slightly. The original model, although really cool looking, right, had this nice scarf, had this nice belt around the hat. Trying to get to that level of detail, it would have made the cycle time absorbently greater than it actually took, and I would have had to go to very small tooling. I am a little limited on my RPM on this machine. So I wanted to kind of simplify it. I didn't need all those details. So I did remove the scarf. I removed the belt. Now, some of the things that the challenges, depending on how the part was modeled, that in this case I ran into, was once I actually removed the belt and removed the scarf, there was holes in the object. It was not a solid object. It was a solid body, but it was actually built out of sheets. So I had to go in and then fill in some of these areas. So those are some of the things that you're going to deal with when you get into some of these freeform models. How do you kind of lace and repair lacking surfaces or how surfaces merge together? Then I wanted to orient it in the same way it's going to orient in the machine. So if you look in here inside of my virtual machine, you can see that I'm going to set up the part aligned to the x-axis, right? Because it's on my rotary. My rotary is an A rotary. So you want to do that right there, right off the bat in your cam system. A lot of people will not align it and then try to handle it later down the road. You can do it, but it just makes a lot more complexity. So I find if I can position the model 0 location, which I worked my 0 from the bottom, and oriented it where in this case it matched my reel. So the object is sitting in a negative x direction and the coordinate system is dead center of the part. It just makes machining it a lot easier. From there, I then had to look up and think about the different strategies of machining. Now, you would assume you're going to go right into a full 4-axis, spinning that rotary around, cutting this part. But, it's the old KISS principle, right? Keep it simple. So in a case like this, you're going to actually leverage 2 strategies. Traditionally, we would do what we would call like a 3+1, where I would go and machine and then position the part with my rotary and then machine some more to kind of rough it all out. And then I really reserve those more complex, full, potentially 4-axis motions for my semi-finishing, my finishing ops. So if you look at my operations, I came in and I started doing kind of like planer milling. So first I approached it from the top, then I spun it to the side, flipped over from the bottom, came up. So each of these operations, it looks like, I'm coming from underneath, but this will trigger the system to rotate the rotary. So the way it works is you're just going to set up a plane, and a plane will drive the rotary. So my coordinate system's staying at the top all the time, but I then establish a plane to say, okay, well, my tool direction and my construction direction is actually coming from the back or from the bottom, right? So you will have to start to get used to working with planes if you're kind of making that move from a 3-axis world into more of a 4-axis machining world. Later, I then get into my full 4-axis motion where I'm actually maybe spinning the tool around the part. So to give you an idea, in the cam system, you're going to see kind of the tool wrap around. In the real world, we're actually spinning the part. In this case, then I'm going to start leveraging some more of these advanced tool paths. And then the plane setup, as I just mentioned, that's going to be a little different because that's going to stay on the top the whole time. So if you look at your plane setup here, now each cam system will do this a little differently, but it is pretty common, technique. So there you see top, top, top. Everything's staying from the top, and now the tool path is what's driving the rotaries around. I'm not spinning the rotary by having to establish a different plane. So once I kind of came up with my strategy, then the next step I wanted to do was actually validate my tool path and get a scenario where I could be really close to the reel. Now certainly I could have, modeled up the chalk, modeled up the 4th axis inside of Mastercam. However, the one thing that your cam package is going to lack that we have inside of this software, and show you, like, here's my machine. Looks a lot like my real machine, intentionally so. The one thing that the cam system doesn't know, that the software knows, is it doesn't have the brain of the CNC, which we call our NC kernel, driving it. And that's a critical point, especially once you get to rotary toolpath or motion, because if there's any areas where the system could potentially interpret the command differently, I may not get a true one-to-one simulation to what's going to happen in the real. And in fact, this perfect example of that I ran into was when I first set up and started outputting my 4-axis motion. I realized quickly that my rotaries were spinning an opposite direction in the reel than they are inside of the cam solution. Now, it was a pretty simple change inside of cam. There's a machine configuration that I went to and I flipped the rotary. But had I been relying solely on the cam system, I would have never noticed that until I got down to the floor. I could have even crashed because it really presented the wrong surface and then she came in. So those are areas where leveraging the software becomes very beneficial. Now, additionally, it allows me to kind of do a full proof of concept. I can set up all my tool configurations and really know kind of what my toolpath's going to look like before I cut my reel. But what's cool about this, and what allowed me the ability of kind of using this in a validation process, is one of the things we can do inside of my virtual machine is we can actually export STL files. So initially, when I printed this is printed on my little Elegoo 3D printer in the back. You would think, oh, Chris, you just pulled this right from your CAD file and walked over and printed it. I did not. I wanted to kind of get an idea of what were the effects of my toolpath on the part, so I could get a little bit more of a one-to-one to what my reel was going to look like. You know, when you're staring at the CAD system the whole time, you're like hyper zoomed in on these little tiny features. So in this case, there was a little ridge, which I can actually feel on this part, where I had like a difference of blend between my 1/8 inch tool and my 1/4 inch tool. I machined the barrel of the body with a 1/4 inch ball end mill, but I machined the face because of the detail in it with an 1/8 inch ball end mill. Now, I was thinking this thing was going to be like staring out like a sore thumb, but the reality was, once I printed it and then finally machined it, yeah, I see there's a little tiny ridge, but you can almost not even notice it in the final part. So it's really nice to get an object that you can kind of validate through the process. So inside the software, once I've machined all my toolpath, I just go to options and say save in process. And that's going to save and make a file in my library under my blanks. So you see here I did a few different ones. Some were at finish stage, like that one. Earlier I did one that has just been the roughing tool operation. But I can export that model, and I export it as an STL, bring it over to my slicing program, come up with a simple little strategy. Now, there will be differences, right? Obviously, the resolution of the 3D printer is nothing like I'm going to get on a machine tool. So expect that. You know, here I got some ridges where it looks like probably I had a little heat deviation when it was laminating the layer. That's not in the reel for sure. So, you know, you're going to take everything, you know, for what it is. But to be able to have an object and to be able to throw it on the printer, let it print overnight before I even set up and cut the first one, I find to be certainly very beneficial. So it's just something that you guys can think about in your processes moving forward. So then, once I kind of flowed through, structured my toolpath, evaluated it, I was ready to set up and run. Now, when we get to the setup side of things, and I'm going to maybe switch this out to just machine view. When I get to the setup side of the scenario, there are a few things that you're going to have to think about when working on a 4-axis machine. So one, a common practice when machining on a 4-axis machine is, oh, wrong screen, is I want to work from the center line. Remember, you saw quickly in the coordinate system when I was showing the part that my coordinate system was aligned in the center. So what that means is my material I'm cutting, where on a 3-axis traditionally would be in a negative direction, on this scenario it's all in the positive. So you got to be careful when you have clearance planes, retracts. You got to remember, hey, I got a 2.5 inch bar. That means that I have 1.25 inches of material in my plus that I always have to account for. The setup is a little different too, right? I'm not just going to come down, hit a top of a surface and set a 0. I have to find the center of this 4th axis, and I have to find the true center. So you want to be careful when you just put a piece of rough stock in here. One, I probably don't know the true diameter of it, and even if I mic it up, how round is it? It's rough stock, hasn't been machined. Additionally, once I go into that, is it running concentric? Yes, I can throw an indicator in and try to square it up. But all of these things, if I don't address, are going to skew where your center line in the Z-axis direction and the Y. Those are the two critical axes where that center line is. So what I like to do is I'll use like a little standard. So in this case, this is actually the back end of a boring bar I cut off years ago because it was too long. But what's nice is it's ground, it's round, it's perfectly 1 inch in diameter, and it's concentric. So if you can, and you have something like this, chuck that up first and use this to do your initial alignment. That's going to get us to the best possible scenario of finding center line. Outside of using maybe like a kinematic alignment routine where I would set a tooling ball and I measure a bunch of coordinate locations. Now when you do your setup, it's going to be in a couple basic steps. So finding the X and the Z and the Y center line is really 3 steps. So first I'm going to set the Z. So I'm going to come down. Now keep in mind, I said I'm working from the middle. This is a 1 inch diameter. So I'm actually touching off to positive a ½ inch. So I'm going to just eyeball my probe somewhere in the center, touch off and give me an initial reference point. I'm going to go into obviously the cycle in our control to do that measuring routine. That, once I have an initial reference point, now I'm going to use, there's a cycle within the system, and we could just jump over here to show you. There's a cycle within the system for measuring that allows me to take 2 points, 2 measuring points, and whatever's sitting in the middle would be effectively assigned 0 or whatever number I have in there. Now when I do that measurement, what's the most critical of that is that I want to make sure that I'm coming down and hitting the same point in Z before it moves over in Y. If you were at a different Z linear position, right, you'd hit a different point on the radius. Now you're not calculating the same center. So that first hit was just to give me some kind of reference. Now if you can, I like to get the sphere of my probe right on center line. So what that means is I would move down to 0 because I set this to top, positive 0.5. And then I would even take into account the radius of my probe, right? Usually around 6 millimeters, so half of that. And I can move down in a negative direction to even get to the center of the probe. From there, I'm going to then hit on both sides, set the middle to be 0. Once that's set, come back up, move the machine to the new found Y0. Now you're truly dead center over the part, and do 1 extra Z hit. Now you know the top is truly set to your positive ½ inch. Then from there, you got to set your X. Now the X position is pretty simple. In this case, since I worked from the bottom of my part, my rough stock was out 4 3/8 of an inch. So I came to that edge, set that surface at a negative, because all my part is sitting in a negative direction of X. The beauty of 4-axis machines, though, is once you've accurately found the center line, now you don't have to find it every single job, right? As long as that rotary table wasn't removed or wasn't hit or bumped or anything, that center line's a constant. So now as I move from job to job, I would typically only need to work or set the X. Now when we get into another strategy, which is called dynamic fixture offsets, that would be where I would be positioning a work coordinate somewhere off the center line, and as the rotary spun, it tracks. Well, it's a little different setup, and we are going to get into that, not today, but keep an eye out for some upcoming YouTube lives. We're going to set up like a tombstone and kind of show you how that mechanism works, because that's a different strategy of setting up on a 4th axis. And I would normally use that if I had maybe not a round part, maybe I was holding it in a 4-jaw chuck, or I had some kind of a fixture and I had multiple parts on this tombstone, as we call it, on this fixture, and then I want to track that 0. So we'll get into that at a later date. So once the system is set up, now we're ready to start running our programs. Now I did something a little unique in this job. What I did was I output a main program, subprogram. Now the programs I'm using will be available to you after the event. There's going to be a link there. There's a link in the description now, just says they're coming. I'm going to pull out all of those right after the event. So you will be able to pull down all these programs. So when you look at the program structure, here you'll see I have individual operations for each of my path strategies, right? So I have op1, that lines up with the cam system op1, I have op2. Let's go to a little closer view so you can see it, all the way up to operation 14. Now, these have been posted as full standalone programs, so I can go into any one of them and you'll see tool change, work order call, everything that needs to be done to make this program run is in there. So if you're not running on a Cinemeric or you're not comfortable with this main program, sub-program structure, and you want to cut the part, you can just run each program individually as their own op. But what I wanted to do was I wanted to create something a little more sophisticated. I wanted to now call up the subs as a call into the main. So what I did was I created a little main program, but this one's a little different. So if you've ever done any kind of main program, sub-program structure, you'll have noticed you'll have a call command right there, and you'll have to have a call command for every single operation. The downfall with that is now I have to edit my main every time I go to do a new job. Well, I tend to be a little lazy, right? So I don't want to have to rewrite my main every time. So what I can do is I can get into kind of what we call variable-based programming, and I can actually force in a string variable in my call statement, and the string variable set up there sets the name, and then I use a user variable or an R variable to index a counter. So I can effectively, every loop of this program, change the subprogram I'm calling. So this program will work as long as I follow a simple structure. This will work on any scenario I have. So what is the structure I built? Well, first thing you got to tell me, and about the only thing you really have to edit in the program, is the number of operations we're going to be running today. So it's always going to start from op1, and this would be your last operation, right? So there's your op4 scenario. So in this case, I'm telling it, hey, I just want to do 4 operations. From there, when you look at the naming convention, I do have to name them all OP underscore and then a number, starting with 1, consecutively getting larger as I go. As long as I comply with that, then the system's going to do everything else automatically. Now, what's also interesting here is I've leveraged what the industry calls structured programming. So not only does the system automatically index the call, but it's also tracking the last program I was in when I was running. So if you do a program interruption, what will happen is the system will go over and set this R variable. So the last one that I ran was actually sub-program number 3. System automatically set that for me. So if I go into the program, right, let's say we go over to auto, nope, I want to get into the main, and I go to run this job, first thing it's going to do is it's going to evaluate that user variable and say, hey, last thing you did was operation 3. Is that where you want to start from? If it's not, all you have to do is go over to user variable, reset the program, set the user variable to a number outside of the total number of operations. So normally I would set this to 0. But what we did do is I set up the logic so, let's say the last time I ran a job, it sequenced all the way up to 10. Well, it knows it's only ever doing 4 because of that variable. So if it sees something outside of those numbers, it just automatically clears it. So by doing that, and I run the program, it's automatically going to start from the beginning. In this case, it's going to go grab my roughing tool and start roughing the first operation of the part. Now, if I want to do a mid-program restart, and I had been running different operations, then I can either go and manually set this to whichever op that I want to run, say op 3, and then when I go in and run it, now it's going to say, hey, that variable is set to 3. That's telling me that the last operation you ran was 3. Do you want to start from that one? Yes, I do. Cycle start, and now it's going to move the rotary. You guys can't really see it. Let me go to this one. So it spun the rotary, come down, and now it's starting to cut that given operation. So it's just kind of a clean way to start working with these mains and subs. If you're interested in that kind of programming logic, what I would strongly recommend is come and attend our level 4 class, our advanced programming class. We go through this whole heavy detail. It's a full 5-axis class, completely complimentary class. Go to our CNC for You website, There you can see and sign up if it's something that interests you. Okay, so now as we start running the program, now is where I'm going to start to look at some of the kind of the unique things I have to kind of look to get into when I get to 4-axis stuff. Now in this case, here we're just running that 3+1 strategy, right? So it's positioning. So, you know, if you're familiar with 5 or 4, or if you're familiar with 3-axis programming, this is effectively all the same. Just you got the stock or the material running in a plus direction. When we get to running with the 4th axis, which is really what we wanted to talk about today, now there's a couple things that I have to be aware of. First thing I got to think about is what we call our feed groups command. So feed groups, when you start to use, excuse me, I was doing pretty good. Feed groups, when you start to use the rotary, right? So let's say for argument's sake, I'm going to go into, I don't know, we'll go into up 5. That's the body where I'm machining the body. When I'm starting to use the rotary for calculating and effectively driving my feed rate, I need to make sure that the rotary is part of the feed calculation. And that's done by using a feed group command. Now, we need to leverage the feed group, and we need to leverage what we call an FGraph or feed graph reference. This is a pretty big program, so it just took a second to load up. So when you get to 4-axis machining with the 4th axis, we then want to make sure that the rotary is part of this feed group statement. And that's where it's important to have a post that's already been developed for this type of toolpath. Now, just by putting the rotary in, that's not enough. You then also have to set a feed reference command. There you can see an FGraph command, right? And that's going to tell me where I am in relation to the center line radially. So if you can imagine, the further out on a radius I go, if I'm telling it to go 5 degrees, the distance the tool is moving is much greater. So that's where all these calculations come in. If you don't put this in, then your effective feed rate is not going to be correct. This is how we start to calculate it while staying in a feed per minute strategy. A lot of controls back in the day before they had this capability would use inverse time. You can absolutely still use inverse time here, but now it's extremely complicated because you're getting different feed rates on every single line of code. Good luck ever editing feed on the floor with inverse time. So I would strongly recommend moving in this direction. This way I'm staying in a G94 feed per minute scenario the whole time, but I'm getting the proper calculations. Now the second thing, yes, Danny was just asking a question. He's on here, yep. Okay, so Dan said the question came in from the audience where they're asking, how do I know what axes to put in the feed group? So I would say in a scenario like this, you want to put all the axes. Traditionally, I never see any benefit to excluding any one of the linears. So if I know I'm doing 4-axis or I'm machining with my rotary, put all of them in. Now the naming convention can get a little interesting. So I would say, check with your OEM or somebody that knows the control a little bit detailed just to know the syntax, because there is a machine parameter in the system that controls that. In my case, my machine, I had to put X1, Y1, Z1, but just A for the rotary. There's a machine naming parameter that comes into play. Okay, so you do the FGraph, you do the feed group, that's going to start handling our calculation. The other thing you got to be careful of is there is a scenario that can come into play where I end up at some point in time just getting a rotary move by itself. Now, when this occurs, the system automatically switches time base to degrees per minute. Problem is, especially in inch, it's very noticeable. If I'm moving along at 100 inches per minute and then I switch to 100 degrees per minute, the machine's going to start going really, really slow. So it's important that your CAM system recognizes this scenario when I get to a point which the system is going to just move the rotary, and I calculate the feed rate relative to a degree feed rate, and I plug that in. Now I'm using FB because this is a non-modal feed command. So in fact, I would not need to repost the feed rate. In this case, we did it anyway as a little redundant, but I would not need to repost it. It would only use that feed for the length of that move, and then automatically the next move switch back to the original feed rate. So to give you a little example of a little more sophisticated toolpath as we wrap up here, I can take a look at my system, right? And let's say I go into, this nice little morphing toolpath. So this is traditionally a full 5-axis toolpath. So let's just jump over to, wrong screen. Jump over this so you can see it real quick. So this would be a traditional 5-axis toolpath, but now we're going to leverage a morph toolpath, or a guided curve, some people would call that, similar to a guided curve, but just for a 4-axis solution. And now all those things are now in play. It knows the feed group and it knows the F graph. So on the machine, we can go over and start to run it. So in the simulation in my virtual machine, I can go to, that one was op8. So since everything works off of the number index, I can just drive right to op8 and we could run it directly. I think this is still running, yep. Or I could run it through my main program subprogram call. You'll get a chance to kind of see what the toolpath will start to look like. So in the virtual, get my cursor back, we'll zoom in a little bit. You can see it there. And in the real, we'll go to op8 and you can see it running. Okay. Got a quick tool change to go through. And this one would be a true 4-axis simultaneous toolpath. You see all 4 axes are running as we roll around. Now the only other thing that I had added to the part, I did want to do a little engraving. So we have our little Merry Christmas 2024 logo right here. This is the only feature if you are going to grab the programs and run it maybe on a non-Siemens system. You know, you'll have to do a little light editing in the G-code, but it's going to be a pretty easy lift if you're going to want to try to run it on maybe a FANUC or a Haas control. This one I did do in ShopMill. I did use our tracehill function to do it. So that's about the only feature that you probably won't be able to run on your system if you're not running a Cinemeric. Hopefully you are running a Cinemeric, and then you can even run that. But all of them will be bundled up for you in the lower section. So Dan, I did want to switch back to you real quick as we're kind of wrapping to the end of this thing. Were there any specific comments or questions that maybe you didn't handle directly that we should address? Dan's just talking to me in my ear, so give us 1 second here. So I do see a few cycle time guesses. So Frank guessed 4 hours, Lazar guessed 1 hour 30, Dan was at 3 hours. Dan, you're not allowed to guess because you know how I programmed this thing, and you still guessed wrong. Kevin was 5 hours 21 minutes. So at the end, I believe I was just sub of 3 hours and 30 minutes to machine this. And the reality was the kind of the time killers is certainly the toolpath you see here. Some of the challenges when you're limited on spindle RPM and I want to reduce my chip load, I'm going to be limited on feed rate, right? So my 1/8 inch tool rolling around the face did take a little bit of time. I did a very fine step over because I didn't want to have to semi-finish and finish. So I roughed it, blocked it out, and then just did effectively just a finishing path with a 1/4 inch ball around the body and around the hat, but with a very fine step over because I wanted to have a minimal cusp height, so I got a nice surface on that. So yes, the cycle time itself was approximately 3.5 hours. Anything else, Dan, that I might have missed? Great. Yep. Okay, so Dasan, I know you guys can't hear Dan, he's in my ear. Dasan is asking, he's a post developer, how does he calculate the F graph? So what you need to do is you need to know where you are in relation to the center line of the part radially, right? So when we did it in Mastercam knows based on my 0 that, hey, when I'm out at the edge of this hat, radially I'm out, in this case, approximately an inch out. So the inch value radially off center line is what goes in the FGraph reference. Hopefully real soon. Our IT has it all now. Sorry, the question, that's one of the things I always mess up when I'm pen in my ear. Kevin wanted to know when our class schedule was being released for CNC for You for 2025. So I believe all that information has been head over to our IT team. So we're just really waiting for them to update the website. So hopefully before the end of the year, but if not, definitely very, very early January, because we do have a class coming out in January. And if you do have any requests, whether it be for yourself or your customers that want to attend some of these classes and you want to attend them sooner, just shoot me an email or anybody in the team an email, and we'd be happy to let you know what the class schedules are. Oh, good. And then Dan added a link to a structured programming webinar we did quite some time back. So if you're interested in how I was doing that kind of main program structure and variable calls, Dan did a really nice event on that. So the link is in the chat. Unfortunately, we do lose the chat once the event closes. So by all means, I would suggest grabbing the link if you want to use it. So with that, we did run a few minutes over. I tried to keep these events around a half hour, but hopefully you guys had a little fun. You learned a little bit. You saw something kind of unique. I really enjoy this stuff. Hopefully you do too. So please like, subscribe, leverage the material wherever you can, and tell your friends, tell your business colleagues, because we want to just keep on producing content. So with that, I'm going to wish everybody a happy holidays. Certainly, I know we have viewers from all over the globe, so whatever your choice of holiday is, I'm wishing you a very happy one, and I look forward to seeing you guys in the new year. So, Happy New Year, and we'll see you next time. Oh, one other thing from Dan. What was that? Oh, we got one last question. Yep. No. So what I would normally do, so the question was, do we update FGraph every time the X and Y axes move? And no, you don't have to have that many FGraphs. What I like to do is I usually set a range. So in the Mastercam post, what we did is we said, once we've set the FGraph, if we see that our reference radius is within a half an inch, we're not going to keep outputting it, right? So as long as I'm in this area and I'm staying within a half an inch of motion up or down, effectively in my Z, right, because that's where it's really coming into play, I would not worry about it. But once I get outside of that tolerance band, then just set a new one. So, if all of a sudden my toolpath, whether it be Z or Y, is outside radially greater than a half inch or around 12 mil, then we'll output a new FGraph. And then when we get within outside of that range, so we just kind of keep rolling it. Okay, with that, I see a bunch of happy holidays. I see a lot of familiar names and faces. So guys, thank you for joining. I appreciate it for sure. And I look forward to seeing everybody in the new year. So with that, thank you, happy holidays, and good evening. And now I get to end the stream. Bye-bye. All right, we are ended. I knew I was going to